if this is VBE, that's IC for this NPN transistor. The curve looks like this, and that's the threshold voltage, usually 0.7 volts. The thing is, it is able to swing a little bit around 0.7, can be a little bit larger than that. The reason is we are actually utilizing that gain here. So for example, it's a very large slope here. If your VBE swings like that, like a sine wave, VBE swings a little bit here, then you are getting a pretty large gain here for the IC. You see that? It's actually amplifying your IC. Has to follow the curve. That's why when VBE swing a little bit, IC swings a much larger scale. So that's why you can get a amplification. And usually if you are talking about the DC biasing, we just treat it as 0.7 volts because the AC change here is tiny. We'll just ignore it. But whenever you are being asked to calculate VBE, you definitely cannot just put a 0.7 volts here, right? It has to be from this equation. That's how you calculate VBE. It's from physics. I don't even know how to derive it. It's from the quantum mechanics. A lot of other equations. It's already 20 years ago when I was in college. But anyway, we don't need to derive everything from the very beginning. It takes a week to just directly use this equation. This is how you calculate VB and IC, right? So IC equals to VBE over VT. And we can get VBE. So what is VBE from this equation? So let's move IS to the left side of the equation. So we're getting IC over IS equals to E VBE over VT, and do a natural log on both sides of the equation. And then this becomes this, or this, oh, sorry, VBE VT times so that's VBE, right? So we're getting VBE from here. So what is VT? The thermal voltage. It's 25 millivolts at room temp. 25 millivolts. I just put it here for now. If I find it's wrong, I'm going to correct it. And IS is called the saturation current. It's a constant as well at a certain temperature. So this is a function of what? The junction area. If you have that BJT transistor already fabricated, right? It's an NPN transistor. So the junction area, the cross-sectional area here, is already fixed. You cannot change it after the fabrication. So they are constant. Junction area, or the base. So here's base, right? Here's collector. C, B, emitter, E. As for the transistor, like this transistor. So this is B, C, E. So emitter emits electrons. or currents. Well, actually currents, not electrons, because currents flow in that direction. So electrons flow back. Or the base width. So here, the area here, and temperature. So we treat it as a constant when we're doing the calculation in BJTs. And before we do the calculations and give you more examples, so let's review these parameters of the BJTs. Okay, here's a BJT transistor, and we're not going to spend a lot of time on the physics and AC properties of this transistor, but just the DC. So here's IB, and that's IC, that's IE. You'll still remember the relationship between these among these parameters. So first, you want to remember these ones, since you are going to directly use them in exam or quiz. Okay, so IE is IC plus IB, which is reasonable because IB and IC are being added together to make IE. And IC equals to beta times IB. So beta is given. That's a gain, current gain of the transistor. You can find out this parameter on the data sheet. If you purchase that transistor, you can find it. IE is alpha times IC, which is wrong. So 1 over alpha times IC. I mean, remember that some standard values. So beta can be 50, 100, or 200, right? And alpha is usually like 0.9 something. Because IE is larger than IC, that's why it's 1 over alpha times IC is going to be IE. That's how I remember that. And two more to make the calculation easier in the future. You don't have to go through this all the time, but you want to memorize it for the first time, and then it's going to be easier in the future. Alpha equals to what? 1 beta over 1 plus beta. You can derive it from here and here. Beta equals to alpha 1 minus alpha. Okay. Be familiar with these ones will make life way easier. All right, let's look at some examples. Yeah, before we do that, another thing you need to know. So usually we have a RB, a base resistor. So RB, if RB is too small, then this transistor will be blown up because it's not limiting. So because here is like a diode, you need a resistor to limit the current runs through the diode. So RB cannot be tiny, like 1 ohms, 2 ohms, probably not. Okay, if RB is too small, blows up the BJT. If RB is too large, then what's going to happen? BJT is off. All the voltage from here will be dropped across RB instead of here. Try to turn it on. So let's look at one example here. If I have 5 volts, that's not VB, that's voltage here, that's 5 volts. And the resistor here is 100 ohms. And I got a 5 volts power supply here as well. So if RB is 1K, what's going to happen? If RB is 1K ohms, since we are doing DC analysis, there's no AC signal, so we can assume here is very close to 0.7 volts. And the voltage across RB is VRB. And what is that? That's VRB 4.3. So IB, the current flows through RB is IB because there's only one branch. IB equals to VRB over RB, which is 4.3 volts over 1K ohms, which is 4.3 milliamps. Okay? So if the beta here is 100, so beta is given, okay? Beta is 100. So we can calculate for IC because IC equals to beta times IB. So IB now is given and is calculated already. So we can find IC. That's the current gain. Whenever you inject that IB in here, it's going to be amplified by beta times. So IC equals to beta times IB, which is 100 times 4.3 milliamps, and it's going to be 430 millivolts. Is that correct? Yeah. Oh, amp, sorry. Milliamp, right? It's pretty large actually when you apply to this one. So that's the IC, that's the current flow through 100 ohms. So how much voltage is going to drop across that? So V, let's call this RC. So VRC equals to 100 ohms times 430 milliamps, which is 430 millivolts or 43 volts. Is that possible? You only have 5 volts here, it's dropping like 43 volts. It's not possible. So what's the problem here? No. So what's the problem? What's happening? We assume it is being operated in this active region, but actually it's not. It's being operated here. So which means the beta is not 100 anymore. But we are assuming it's here, and we are using 100 for beta. That's why we are getting this weird voltage. So see, you cannot make this, so this voltage cannot be too small. No, this resistor, a 1K resistor is too small for this case. Then increase the resistance a little bit. What about 20K? So in this case, how can I fix it? We're not changing RB. So the reason you are getting 43 volts is because this timing is this one times this one, right? So what if it's just 1 ohm? Then you are getting 0.4 volts, right? But it's going to be smaller than this one, so it's still not operating in the active mode. I mean, you can make this a little bit larger, but the problem is it's drawing a lot of current, like 430 milliamps is a large. So amps is a large unit. You know that, right? I mean, how much current can kill a cow? I have been telling my students for a few years, like if you inject that much current through the body of the cow, it can kill the cow. Only 200 milliamps, right? But the skin of the cow has a huge resistance. You have to apply a huge voltage in order to get that 200 milliamps. It's not really difficult. It's not really easy to kill a cow use electricity, right? You have to have a 2,000 volts and huge power supply can supply that much of current. And when you get a static shock, I've been saying it's probably 20,000 volts, but you are not killed, right? And why? The current is low, probably like microamps or something, 1 microamps. It's not really easy to inject that 200 milliamps into someone, but it's going to be a deadly current. So 430 milliamps is a pretty large current. So I have to use a special BJT to handle that much current goes through the collector. It's not a common design here. Usually if you put an RC here, the RC is a load. You can imagine if this guy is a motor, the regular resistance, internal resistance of the motor is just 50 ohms. Because it's just nothing but a coil, right? The coil is just a wire coil, the copper coil. Usually only 50 ohms for that motor as a load. So 50 ohms is a really, really heavy load. You know, it's a little bit different from the common sense, right? Thinking about like 20k ohms is a heavy load, but actually it's not. So whenever the resistance is low, something like a motor, it is a heavy load. So that's why you have to use a motor driver to drive it, to run all these currents through it instead of running the high current from the microcontroller, which cannot handle that much current. Have to use a power device to do that. And 100 ohm is also a very heavy load. It's going to draw a lot of current. Just some examples you need to know. So usually this can be a motor, can be a LED. You turn it on here, it draws a current from here, get a current gain, and runs a lot of more hard current compared to this one. So that's why you can use a low current device, just running logic. You know, just turn it on and off, and you can turn on and off for this high current branch, because usually this is a load. Can be a motor, can be LED, can be a heater, a resistor, can be anything. It's you need more current to run through it. And so what about 20K? If I put 20K here, what's going to happen? Still use the same resistor, but 20K. It's a DC analysis. So we are not talking about the little swing around 0.7. It's still 0.7, very close to that voltage. So IB equals to what? 5 volts minus 0.7 over 20K, which is 4.3 volts over 20K, which is 0.215 milliamps. And IC, which is the current flows through here, equals to beta times IB, which is 100 times 0.215 milliamps, which is 21.5 milliamps. So the voltage dropped across that RC, VRC, equals to IC times RC, which is 100 ohms times 21.5 milliamps, 2150 millivolts, or 2.15 volts. So the requirement to operate this BJT in the active region, if you look at the curve, that's V collector emitter voltage, that's IC, that's a collector current, and that's the active region which you want to operate your BJT at. The requirement for that one is VC is larger than VB is larger than VE. So this is larger than this is larger than this. So you can have that continuous potential gradient to push the current out of the emitter junction. Remember that, okay? So I got 2.15 volts dropped here. So what is the VC? Because VE is grounded, so if I get VC, I know VCE. This is 5 minus 2.15 volts, which is 2.85 volts here in that case. So what is VB? Very close to 0.7. So we are getting VC larger than VB larger than VE. So it's going to operate in the active region, which is good. So compared to the last example, you can find out that if you change the value of the RB, you can change the operation mode of the BJT. RC as well, but usually RC is given. If I plug in a motor in there, it's going to be 50 ohms. You cannot change it. But if you are designing the circuit, you can change it here to get the largest gain. Okay, if it's just being used for the digital circuit, you don't need to run any AC signal to control it, to amplify, to control that motor. If it's just turning on and off, right? If you want to get the most current gain from this BJT, you want to operate this device in the active mode. Here is the requirement. Okay. So whenever in the lab, when you are operating this thing, it's very practical circuit, even though it's very simple. It's very practical. And usually the BJTs can handle larger current compared to CMOS. So the BJTs are often used, often used in the power circuits. So if you are trying to turn on and off a motor, you can definitely use this one. The reason is you can turn on and off the motor using a low current, low power pulse from the Arduino GPIO, right? You can just program it, turn it on and off, do a digital write, one low, high, low, low, high like that. And to turn on this one, use a low current pulse, and it's going to supply a little current to the load. So that little thing is the load. The device is going to drive, okay? If you find out you can connect the current meter in the middle, just break the line and connect the two terminals of the current meter into here. If you're looking at the current it's very low, which means it's not being operated in the active mode. It's probably in here in the saturation mode. So you want to change, modify, have a little potential meter to adjust the resistance here in order to get the highest the current you can get, right? That's a little BJT switch. You can see this kind of switch in a lot of places. The reason I want to cover this is this definitely can be used in op-amps in the old design from Texas Instrument. It's still being used like a 741 op-amps from TI. They're still using BJTs to build the op-amp. Definitely they are not the high-end amplifiers. But also they are being used for power devices to drive a motor, drive any other load in here. Whenever you are seeing these kind of circuits online or from some examples, for your project, can be a junior design, senior design project, you should know what's happening here. They can be used as a switch as well. A few other examples. So if I just make this type of connection, so in the old days, this is an inverter. Can't believe that. Where is the output? So that's a pull-up resistor, let's say 10K. If you give a logic high, like 5 volts, you turn it on, and this pin will be pulled down to the ground, so you are getting a logic low. If you keep this transistor off, give a 0 volts, so there's no current, so there won't be any voltage drop across this 10K resistor, so it's going to be put up to VCC, which is 5 volts. That's literally an inverter for old digital circuits before CMOS transistors are invented, right? So they use BJTs to build logic circuits. So what about this? Where is the output? So what's the logic? Zero, zero, both are off. This will be pulled down to the ground. 0, 1, off. It's just one branch in series, so still off and still being pulled down to the ground. Same. Only when both of them are on, you got a one channel here. It's going to pull this up to VCC. So what is this logic? Yeah. So this resistor is called pull down resistor. We can form a lot of other logic circuits. I'm not going to draw all of them since it takes a lot of time. And I'll just give you another example for the calculation instead. So let's start with this example. NPN BJT transistor. IS is given because as the BJT has been fabricated, so IS is a constant. It depends on temperature. And beta is 100. And the circuit looks like this. That's a current source. (3K). VCC is 5 volts. And that's VBE. And this is a 10 microamp current source as VB. So the first question is find VBE and VCE. Can find these two parameters. How to find them? Let's say this is a PN junction here, so VB is going to be 0.7 volts. No, it's asking you to calculate for VBE. So there will be a little, tiny little bit change around 0.7. So we're not trying to use the 0.7 value. This is not accurate. It's asking you to calculate that. So the equation here is IC equals to IS times E to the power of VBE over VT. So we know that from this equation, we know that VBE is VT times natural log of IC over IS. Is that correct? And VT is given, right? VT is 25 millivolts at room temp. And IC, we don't know. So what is IC here? IS is given as well. So IS is 10 to the negative 15 amps. But IC, what is IC in order to calculate for VBE here? What is IC? So IB is given, IC is going to be, yeah, beta IB, 100 times 10 microamps, so 1 milliamp. You amplify, get 1 milliamp. So you can plug in all these parameters into this equation to find VBE is, I won't do the calculation, but I will just throw out the number here is 0.69 volts. You see it's very close to 0.7. That's why it's asking you to calculate that. You don't want to directly use 0.7. A bit different from 0.7. And the second question, replace the 10 microamp current source with the resistor and 5 volts. So what is R? So it's literally asking for that. If I change the circuit to this, C3K, 5 volts, and I don't know the R. I want to operate the BJT at the same mode, the same current, same IB, same IC. But I'm going to replace that current source with a resistor and 5 volts power supply. This is actually shorting these two pins together, which is fine. So what is R? It's asking for that. What is R? How to calculate it? Because it's being operated at the same mode, which means it's getting the same VBE. So you have the VBE is given because you have calculated already. So VR equals to, we got 5 volts here, and from this node to here, you got a VBE drop. So you can calculate VR, which is 5 volts minus VBE. So R, what is R though? Yeah, you want to use the same IB because it's being operated at the same mode. So the IB will be the same. And now you know VR. So that's because VB is given and you know VR will be 4.31 volts. So R is going to be VR over IB, which is 4.31 volts over 10 microamps, which is 431 kilo ohms. To make that happen, to operate this thing at the same mode. Okay. One more example. The NPN transistor and VBE is 0.7 volts. when IC is 1 milliamps, 1 milliamp. So the question is find VB at IC equals to 0.1 milliamp and 10 milliamp. How to do that? So we didn't learn that many equations, right? Which makes things easier. So that's the only one we have been using. We're going to just use that one, right? So when for the first case, when VB is at that current, so these two are given, and that's 25 millivolts. But we don't know this. And do we need to calculate for that? I'll say, yes, I can do that. I just plug in all the IC, VB, and VTs and calculate IS. And then when I'm trying to calculate the VBE from here, I'm going to list another equation, the same one, and use the same IS in there to find out VBE. It takes a lot of time to calculate in that way. I mean, there's an easier way to do it. Is IS changing for the two cases? No. So IS depends on what? Junction area, the cross-sectional area, and the base width, the base metal contact, temperature. So it's not changing, it's still the same transistor. So we just do this. IC1 equals to IS, IS is not changing, it's all the same, so I'm not having a subscription over here. VBE 1 over VT, VT is a constant, and IC2 equals to IS, VBE2 VT. So IC1, IC2 equals to ISE All right, let's do this. Do a division on both sides of the equation. So canceled. And IC1 is 1 milliamp. IC2 for the first case is 0.1. VBE1 is 0.7 volts minus VBE2. So this is 10 times natural log VT equals to 0.7 volts minus VBE2. Okay? It's natural log on both sides, right? So you can get this equals to this. So you can calculate for VBE easily. So VT, remember, is 25 milli. Right. So that one equals to 0.6. Wait, no. Oh yeah, 0.64 volts. Right. So it's going to be the same way if you calculate VB when the IC is 10 milliamps. The same concept. Any questions so far? No? Good. I have a couple more examples, but I don't think I have time to do it, for the 4 minutes. I'm going to just call it today. That works. Okay.